This is the first part of advanced dimensionality reduction. Here we are using a image dataset, the fetch elevative faces from sklearn datasets. This has 400 face images and 4096 dimensions. The high dimensional image dataset is perfect for showcasing various dimensionality reduction techniques. First, we set up and load the data. Uh, Now we are implementing the dimensional reduction methods. First, we apply the LLE, locally linear embedding. So here is the function for LLE. Next, we work on TSNE with interactive visualization. Here is the function for the same and the graph. Next, we implement the isomap. This is the function. And then we move on to UMAP with the interactive visualization. This is the UMAP with interactive visualization. So as you can see, I had just zoomed into one single point. This is interactive. Next, we do MDS. After that, randomized PCA. This is rand PCA method. And kernel PCA. This is KPCA method. And incremental PCA. So here we have the IPCA method. The ninth one is the factor analysis. This one. And finally, we have the autoencoder. Once the autoencoder is done, we have the visualization function for all embeddings. You can see all the embeddings, all the 10 methods have been embedded. Now we move on to the tabular dataset. Here first we pip install all the required libraries. Then the dataset we are going to take is the diabetes dataset. This diabetes dataset from sklearn would be ideal for dimensionality reduction tasks since it contains medical data with 10 features that can be effectively reduced to lower dimensions. So first, we set up and load the data. Then we do the LLE. Then we go on to do the TSNE with interactive visualization. Next, we have the isomap. Then we have here the UMAP with interactive visualization. Next, we have the MDS. Then we go on to do the random PCA. Then we have the kernel PCA for the same and the incremental PCA for this data. We then do the factor analysis. And finally, we have the autoencoder. Now, going on to the dimensionality reduction using Databricks. So, first, dimensional reduction using Databricks. Dimensional reduction is a process used in data science and machine learning to reduce the number of input variables in a dataset while retaining as much meaningful information as possible. This is especially important when working with high dimensional datasets where many features are redundant, irrelevant, or highly correlated. First, we set up our PySpark in Colab. We install PySpark and unpack it. We install its dependencies, OpenJDK 8 required to run Spark, and install FireSpark library, which helps us to locate and initialize Spark in Python. We set up the environment variables here. Then we initialize Spark. Step 2 is loading the data set into the PySpark. Uh, we will use wine quality dataset. Here we download the dataset, load into the Spark data frame. Then step 3 is pre-processing of the data. Transform the data to a format suitable for dimensional reduction. After we select a few features, standardize the data. Standardization features by scaling them to have zero mean and unit variance of requirement of PCA. Step 4 is applying dimensionality. So to perform PCA using Spark MLIB, uh, PCA projects the original high dimensional data onto 2D space while retaining maximum variance. So yeah, this is the one. Next, we should discuss about the PCA parameters. Here we put k is equals to 2, that is reduce dimension to 2 principal components. Input columns, the column containing the scaled features, and output column, the output where PCA features are stored. Extract PCA results. We convert the PCA transform data into format suitable for further processing, that is visualization. That's the step. Then we visualize the results using mat matplot library to visualize the PCA results. We convert PCA data to pandas, and this is the plotting of the same. Next, we run TSNE. For TSNE or other techniques not available in Spark, export scale data into NumPy and use skitlearn. We install the NumPy library. We can discuss about the TSNA parameters such as n components, which is 2, perplexity is 30, and the number of iterations is 300. So all those are given here, and using this we got this plot. Now visualization, one of the visualizations is two-dimensional Gaussians. To generate and visualize Gaussian distributed data, this is the function, and this is the plotting of the same. The result plot visualizes 2D Gaussian distribution. The points form an elliptical cluster centered around 0, 0, reflecting specified mean. The spread is influenced by a covariance matrix. The positive covariance 0.8 causes the points to cluster along the diagonal direction from lower left to upper right. This indicates positive relationship between two dimensions. Points are denser near the mean, gradually thinning out as they move away, following Gaussian bell curve pattern. Then we write PCA function and evaluate PCA on sample datasets. And this is a visualization PCA projection. These results simplifies the dataset, reorienting it along directions of maximum variance. In higher dimensions, such projections allow us to visualize and analyze complex datasets in lower dimensional space. The projection ensures that minimal information is lost, preventing overall structure of the data. Uh, Three-dimensional data visualization is also required. This plot visualizes three-dimensional Gaussian distributed data generated using a specified mean and covariance matrix. The 3D scatter plot provides insights into how data is distributed in 3D space. The results of this plot provides a clear understanding of how data is distributed in 3 dimensions, useful for exploring relationships between dimensions in higher dimensional datasets. Sets the stage for dimensionality reduction techniques like PCA, which simplify such datasets by projecting them into lower dimensional spaces. Now we go on to the fourth visualization, 2D representation of 3D data. This plot represents 2D projection of 3D data using principal component analysis. The transformation reduces the original three-dimensional dataset into two principal components while retaining most of the variance in the data. This simplification reduces 3D data into 2D representation for easy visualization and analysis. Highlights the directions with the most significant variance, making data more interpretable. Demonstrates PCA can effectively reduce dimensionality without losing critical information. Next is the pixel intensity. And the next visualization is normalized data. This normalized data and two top two components as one image is this one, combine top two PCA components. Next, feature-based aggregation is followed by PCA. The visualization shows PCA projection of aggregation digit features. The dataset is aggregated by digit label 0 to 9, where the mean feature values for each dataset are computed. PCA is then applied to reduce the dimensionality of these aggregated features to two dimensions for visualization.